So we're going to use the PhET simulation to build a circuit again. Let's pull out a cell. I kind of want to turn my cell the other way around. I just like to have my circuit that way round. I'm going to add in some wires here. And I think today I'm going to use resistors rather than lamps. We're going to do a little bit more about resistance of components next week, but for now it's just a convenient component to have there. So here we go then. I've got a complete circuit and I can see I've got my charges flowing around the circuit. I'm showing the direction of conventional current, plus to minus. So here we are then. Let's turn that into a circuit view. You can see that this resistor symbol isn't actually the same as the one that we've learned. This is an old US symbol. We're going to use that rectangle for all of our work in school. So let's have a look then at measuring some voltage. Let's take a voltmeter. Now I know that the red connection on the voltmeter needs to go to the positive of the cell. Let's measure the PD across the cell, the voltage across the cell to start with. So I'm going to put that red connector on the plus side of the cell. I'm going to put the black connector on the negative side of the cell, and you can see there I'm reading 9 volts across my cell. If I move those connectors down to the resistor, again the red towards the side that's nearest positive and the black towards the side that's nearest negative, again I've got 9 volts. And what that tells me is, yes, my cell is giving each unit of charge that leaves 9 joules of energy, but almost all of that is being transferred to other forms in this component. It's a resistor, so it's being transferred to heat. There is a tiny amount of energy that's transferred in the connecting wires, but we'd need a lot more decimal places on our voltmeter in order to be able to actually see that. So as far as we're concerned with the readings we're taking, all of the energy that we're giving to the charge as it leaves the battery of the cell there is being transferred to other forms in the resistor. Okay, so let's now look then at what happens when we've got some more components to play with. Let's disconnect our voltmeter for now. I'm going to take off those current directions there because it just makes it a little bit easier to look at. I'm just going to take away these connecting wires for now, and I'm going to stretch out my circuit so I've got a bit more room. And I'm going to add in some more resistors. So I've got a resistor here, I've got a resistor here, I'm going to put another resistor in here. Let's join that one on there, let's join that one on there, and then we can use some connecting wires to connect them up. So we've now got another complete circuit. So let's see what difference that has on our results then. So let's take our voltmeter and just check again what the PD across the cell is, the voltage across the cell up here, and still we've got 9 volts. Let's take these connections then and put them across the first resistor. Ooh, interestingly now then I've got 3 volts. Hang on a minute, I'm going to check the others. 3 volts. And here we've got 3 volts. So what this means now then is that thinking again about our current flowing around the circuit, we've now got much more resistance in the circuit, and you can see that from the rate that the charge is going round, the rate of flow of charge is much smaller now. But in terms of the energy lost by these charges, for our 3 identical resistors, they lose the first third of their energy in the first resistor, the second third of their energy in the second resistor, and the third third of their energy in the third resistor. So the energy is lost a little bit in each component. The charges, remember, keep going round. So each unit of charge that leaves the cell will eventually get back to the other side. But the energy is transferred in the different components, and each component has a small amount of energy transferred in it. Question that's using the same ideas